All right, hello everyone. So today we're going to be working with a couple problems from multivariable calculus. We're going to go through how you find the absolute maximum and minimum of a function, two-variable function to be specific, over a region such as what we have here. And there's a couple of ways of attacking these problems. It all depends on what you have. So for the first one I have, find the absolute maximum and minimum of f of xy equals e to the xy within the disk x squared plus y squared is less than or equal to 1. So typically what we do is we treat this with, it's like in two parts. You have your region and you have your boundary, or like your border or whatnot, whatever you want to call it or think about it. And then you have your region that's inside of the border. For the inside of the region, you're going to basically, and what I mean by that is the part x squared plus y squared is less than 1. And for the boundary, that's the part x squared plus y squared equals 1. Specifically, that's how we would describe it. With the region on the inside, what you're going to do with that is you're going to find critical points like you typically would do. And for the boundary part, you would use something along the lines of Lagrange multipliers or substitution, okay? So let me go ahead and get to that with this problem. So for the inside, yeah, we're going to use a process that you would use to find critical points for your function f of xy. So f of xy equals e to the xy, and how would you find critical points in multivariable calculus class? Take your partials x and y, set them equal to 0, and solve, and you get a point here 0, 0, okay? Now, I don't need to actually classify this point. I don't need to say it's a relative min or max. That is not our concern here. Just need to grab the critical point. All right, for the next part, so that's like for the boundary, you're going to use something like Lagrange multipliers or substitution. Now, which one should you use in which case? It depends. If you have something fairly straightforward as an equation that describes your boundary, then I often tell people I would use Lagrange multipliers, okay? So this is a case of that. Now, it's easier to see what my advice, it's easier to see how it would apply with the next example that I do, okay? We'll get to that in a minute. But with Lagrange multipliers, right, you have a function that you're trying to optimize over a boundary, over a level curve. In this case, that would be the x squared plus y squared equals 1, and we're just going to call that g here. And yeah, I take my gradient of f equal to lambda times the gradient of g, and we consider the level curve, x squared plus y squared is 1. And yeah, I did some work here. And yeah, my focus today isn't really to look at like the computations, but in order for me to be transparent, just to get an idea of what I did, I like to kind of just show you the steps here. And I'm going to go ahead here and work with this system. Let me highlight that right here. The system that I'm working with is y e to the xy 2x lambda and x e to the xy 2y lambda. Yeah, and I'm working with that primarily because I want to get some relation between the x's and the y somehow. And what I did here is I divided equations 1 and 2, where x doesn't equal 0 and y doesn't equal 0, right? Because we can't divide by 0. And you get this relationship, x squared is y squared. I substituted it back then into that level curve. Typically, that's what we do. We find a relation between x and y, plug it back into the level curve function. And I'm not going to go into, again, all the details. And you get actually these 4 points, okay? And what you're going to do is you're going to take those 4 points that we just got, along with the point 0, 0, and you're going to plug them back into your function. So you're going to place back all points from the inside and the boundary into the function that you got. And this is what you would get. You would get these values, and the absolute maximum would come out to be e to the 1/2, and the minimum would come out to be e to the negative 1/2, okay? All right. So that's how we handle that situation. Now, a situation where maybe you would not use Lagrange multipliers would be something along these lines. I'm going to ask you to find the absolute maximum and minimum of the same function, exy, inside this region, though. This region, though, is made up of basically these line segments, and you make a triangle, okay? And in terms of finding like the points on the inside, I would do what I did again here in terms of I took my partial, set them equal to 0, and you get 0, 0. But this is really important. And maybe I should have mentioned this when I was doing the first problem, going over the first problem. That point needs to be inside your region. If it's not inside the region, we're going to discount it. But so in this case, you get 0, 0, but it is not in the region that we are speaking of here. So we're not even going to take that into consideration. Now for the second step, like I did previously, for the boundary, I'm going to consider either Lagrange multipliers or substitution. I would not use Lagrange multipliers here. I would use a substitution, because your boundary is made up of 3 multiple lines, and you can think of it as 3 multiple functions. So yeah, technically you could apply Lagrange multipliers, but it's really it's not going to work out nicely, put it that way. So basically in a case where you have a boundary made up of different curves, I would suggest you use substitution. And what we're going to do here is, and if you allow me, I'm going to go back to our picture that we had a second ago with the triangle. I'm going to substitute the red line, the green line, and the blue line at different times, okay, into our equation. So the red line is a non-horizontal vertical line, so it has a slope, and you can figure that line out to be 2x minus 1 by finding the slope of the line. And please note that I'm going from 1 to 9 on there, so I'll let you look at that picture for a second. And yeah, all I'm saying is I'm considering the red line from here to here. So we substitute in y equals 2x minus 1. So I'm going to replace all my y's. And the idea here is you get a function of one variable that you're optimizing in a closed interval from 1 to 9. So, you know, what does that entail is where you have to kind of go back to your calc 1. You take a derivative, set it equal to 0. You get 1/4. But see, x equals 1/4 is not in the region, so we're not even considering it. Next, I would substitute y equals 1. So it's the green line. And you get e to the x, same thing, take the derivative of e to the x, you get 0. No points, basically. And finally, I would substitute x equals 9. And I would get f prime equals 9e to the 9y. You get equal to 0. There's no values here either. So no critical points, none. Technically, that's what's going on, really. However, does it mean we have no mins and max? No, we don't. Here's what we need to look at. We're looking at these lines that we had drawn earlier, and see, we're looking for the min and max of, let's start with that red line from 1 to 9. So we were considering the closed interval of 1 to 9. So if you recall from calc 1, if you had a closed interval, you could have critical points on the end, the mins and maxes. The absolute mins and maxes can happen at the end points, or they can happen in a point in the interior of that interval. Okay, so in so many words, the endpoints of the intervals for us here are the corners. Those points would be 1, 1, 1, 9, and 9, 17. So at all these corners, you can have a min or a max. Okay, so those are the points that you would be basically considering. And yeah, I'd put these points back on my function and see which ones give me my min and my max. And in this case, my min is e to the first, that's like 2 and some change, and my max is definitely e to the 153. I have no clue what that is, but that's definitely the biggest value. Okay, so 2 different problems with 2 different regions that we're trying to find the minimum and the maximum of. One was a nice curve in the sense of, like, yeah, you can represent the whole boundary with one equation, and another example where the boundary had to be described with 3 equations, so that was a little tougher. So as I said, also Lagrange multipliers work out pretty well when you have one equation that describes your boundary, and when you have multiple boundaries, it's easier to use substitution. Well, thank you so much for your time, and I hope this helps.